is we are going to derive these equations, the governing equations, one by one. The first one of them is continuity equation, the second one is momentum equation, and third one is energy equation. Okay, and momentum equation will have 3 parts, so total there will be 5 equations. Now continuity equation is actually representing one physical law, that is mass of the fluid is conserved. So this is the basic law which is represented in form of equation here. Now what does that mean is that the difference between mass of the fluid leaving the control volume and mass of the fluid entering the control volume is equal to the net decrease in the mass of the fluid stored inside the volume. This is what the continuity means, or the conservation of mass means. Okay, so if suppose you have a block like this, right? Now mass here is, first is m1, and then you have mass that is equal to m2. Okay, now from here a1 has gone out and b is gone in, which means that m2 will be equal to m1 minus a1 plus a2. This is what it means. Okay, so we have to derive this equation. First of this we will consider a control volume. Okay, we can have any one of them, control volume or control mass, but we are starting with control volume. Now in a control volume, shape and the position of the control volume remains fixed, right? As a result, and fluid flows in and out of the control volume. So we recollect the definition of control volume. It is fixed in space, but it is having open boundaries, but the boundaries are fixed, right? Open and rigid boundaries, fixed boundaries. Okay, now if this is the shape of our control volume. Okay, mass is entering here with velocity u, and it is coming out with the velocity u plus del u by del x into delta x. Similarly, mass is entering here with velocity w, and it is coming out with the velocity w plus del w by del z into del z, delta z. And similarly on this face, which is the front face, mass is entering with velocity v and going out from the back face with the velocity v plus del v by del y into delta y. This is how the mass is flowing. Now if we look at the volume of the control volume, it is equal to delta VL is product of delta x, delta y and delta z. Okay, now we find out what is the mass of fluid entering in the control volume. So mass in will be equal to the mass flow rate per unit time into delta t. So we are considering interval delta t. Now what is the mass entering in rho u? It is from the left face, rho u into delta y delta z. What is entering from the front face is rho v del z into delta x. What is entering from the bottom face is rho w into delta x delta y. And then you multiply by delta t, that gives you the total mass which has entered in time delta t. Now then we calculate mass of the fluid which is leaving the control volume. Now again that will be equal to m out, that means the mass which has flown out is equal to m dot out into delta t, that is rate of mass flowing out into delta t. Now this is the rate of mass flowing out, right, into delta y delta z from the right face. From right side this is how the mass will flow out, from the back side this is how the mass will flow out, right, and similarly from top face this is the mass which will flow out. Okay, you could have taken it like, you must be wondering that you could have taken it as rho plus del rho by del x into delta x into velocity will be u plus delta u by delta x into delta x into delta y and delta z. Okay, and this is same as this, because when you do this operation there will be there will be 4 terms here. One will be this term, one will be this term, then there will be this term, and there will be this term. So there is a one term, then you have second term, you have third term, and you have fourth term. This fourth term will be negligibly zero. So you'll get 3 terms, and this is same as this. Okay, fourth term is negligible because delta x is coming twice. Okay, so I have written it briefly that you can hide this. Same applies to others. Huh? Is it clear, or should I do the more of mathematics? Okay. So this is what is mass flowing out. Now what you do, you find out what is the increase in mass of the fluid in control volume. M2 is the final mass, M1 is the initial mass. So this is how much the mass has increased, and this will be equal to M in minus N out. Whatever is going in is increasing the mass, what is going out is decreasing the mass. So it will be M in minus M out. You can also write M in dot minus M out dot into delta t, because duration will be same for both the things. Then if you want to find out what is the net increase in the mass of the fluid inside the control volume. Now one thing is there, that volume of the control volume is not changing, its boundaries are fixed. So this is the change in the mass of the control volume. This is the volume of the control volume, and this is del rho by del T into delta T. Volume into change in density, that will be the increase in mass. Okay. Now we equate all these terms. So this m2 minus m1 is equal to this. Okay, and we can write it, when you solve this you will get this term. Okay, we need not go into the mathematics of it, that you can do at your convenience. Okay, you have to go by faith here. Whatever I written is well checked many a times. Okay, so this is the equation which you get, and what we do is we cut out volume and delta T from both sides, right? So you get this equation, finally del rho by del T and these three terms. Okay, if you want to put it briefly, it is like this, right? Now the first term, what it is representing, this is the first term. This represents rate in increase in the mass of the control volume. At what rate the mass is increasing of the control volume? Per unit volume of the control volume. Mass increase per unit time per unit volume, that will come out to be density per unit time. Okay, and what is the second term? Second term represents rate of mass flowing out of the control volume per unit volume of the control volume, right? This is telling you what? Del rho u by del x. It is telling you difference in the mass flowing it from the left face and the right face. So del u by del x is saying that how much will be more on the right face. Similarly, del rho v by del y is telling you how much will be more on the back face, and del rho w by del z is saying how much will more be on the top face as compared to the bottom face. So this is talking about difference. So this is telling you the rate of mass flowing out of the control volume per unit, and we should write it net rate. Okay, something is going in, something is going out. The difference between the two in terms of how much is flowing out, that is the net rate of mass flowing out per unit time per unit volume of the control volume. Okay, so this is the equation you get. This is a continuity equation. Simple. This is simple continuity equation. Okay, now this equation can be put in two forms. One is the conservative form, and there is second is non-conservative form. There is some difference between the two forms, right? We will discuss this later on. Once we have completed all this, we will see that what is the basic difference between the two. Mathematically, there is no difference. Whether you take the conservative form or the non-conservative form, mathematically there is no difference. But when you discretize the equation, the two equations are different. their results are different. Okay, and both of them are useful. In certain cases one form is useful, in the second case another form is useful, and that is why both of them are prevalent, both of them are being used. Otherwise mathematically they are same, you could have used any one. Okay, so we will talk about it later on, that what is the advantage of this, or what is the difference between the two, okay, physically. At the moment you can say that which one is the conservative and not. So this equation which you have got is already a conservative form. This is in the conservative form. In the conservative form, that all the derivatives are inside, all the parameters are inside the derivative. Okay, this is one broad difference. You can see that visible difference to find out that whether the equation is conservative or non-conservative. That doesn't mean that it is following, one is violating the law of conservation. No, that doesn't mean that. Okay, we will come to that later on. Now this equation, which is in the conservative form, can be changed in another form by doing simple mathematics operation, and what you get is called the non-conservative form. So what we do, we break up the second term here like this, and it is simple. Derivative of product is what? Derivative of A into B is what? Derivative of AA into B plus derivative of B into derivative of A. Okay, one by one you do, maintaining the product. Same thing is done here. Once V is taken out, the other time rho is taken out. This here you can prove mathematically, because actually this thing is, there are three terms here. So if you want to write what is this is del by del x of rho u, comma del of del y of rho y, comma del by del z of rho w. Okay, so and you can break each one of them separately, right? So what you will get this. So what do? We take the original equation and replace this term by this. Okay, now now we also know from our previous article that how do we solve this substantial, local and convective derivative, which we have already done. It is written like this. So total derivative of rho is equal to local derivative of rho plus convective derivative of rho. Okay, and this term is same. So what do you get? You get actually this, because what will happen, these two terms right here, they will add up and you will get total derivative. Now if you see this equation, rho is outside the derivative, v is inside the derivative, and that makes it non-conservative. Okay. So there are two forms of equation, this continuity equation. One is you have the conservative form, one is the non-conservative form. Again repeating that mathematically both these equations are same. We have achieved one from the other, and we can go backward, we can achieve this first one from the second one. No problem. No assumptions, no special laws. Simple mathematics. Right? In one case, the parameters are inside the derivative, in another case, parameters are outside. Now, these two become exactly same when we talk in terms of derivatives. No doubt. The moment we discretize it, right? Because discretized equation is not same as the original equation. Remember, when I talked about the errors in CFD, I told you that there is something called truncation error. Why the truncation error comes in? Because when you take up an equation which is a differential form, convert it to algebraic form, right? Then if you want to be accurate, then there will be infinite number of terms. Because you are leaving the certain terms, right? So what happens is your algebraic form is not exactly equal to the original equation, right? So if I may write like this, you have conservative form, you have non-conservative form. As far as the differential form is written, this is exactly equal to the differential form. So on one side you have conservative form, on the other side you have non-conservative. And once you write the differential form, both are exactly equal. Now you break this, you get a algebraic equation plus some delta 1. On this side you get algebraic equation plus delta 2. Same. Now what you do, you ignore this. You ignore this. So you get AE1 on this side, AE2 on this side. Now these two are not equal. The terms which are in part of the truncation error, they are different. So in a limiting case, both are equal. So if I want to write delta, you can say delta x, comma delta y, comma delta z, comma delta t. If all these are approaching to 0, then AE1 is equal to AE2. Right? But if they are, because obviously we cannot have the infinitesimally small element. That is a limit. So the error will always be there between the two. Okay? So this is how the two equations are different. Now we proceed for the second equation. And again, as I told you, there are three equations. We'll be proving only one. The remaining two are similar, so need not worry about it, because writing all the three, doing mathematics for all of them, it will become long. So we avoid doing that. Now again, what is the physical law which is governing this equation? Okay. The physical law is that the momentum is conserved. This is what we know as Newton's law. Right? The momentum is conserved, which in other words will means sum of forces is equal to mass into acceleration, right? And momentum being a vector term, it can be divided into three equations. For x direction, sigma fx is equal to max. For y direction, sigma fy is equal to may, and for z direction, sigma fz is equal to maz. We will be using only one of them. Okay. Now then, so we will be working on this equation. Now what we do is, we take this forces acting on it. Now what we are doing is, here in this case we are going for, let me check, control mass system. Earlier we were using control volume system. Now we are shifting to control mass system, and it does not make a difference. It is how we are looking at the fluid. Okay. So this is our control mass, which means that boundaries are flexible, but impervious. Boundary is flexible and impervious. Now if you look at this block, all the forces are shown here in either x direction or minus x direction. Okay, we need not bother about forces in y direction or z direction, because we are only talking about conservation of momentum in x direction. Okay, so all these forces A, B and so on, all of them are in x direction. Okay. Now what we do, first of we calculate all these forces, and there are total, we go up to GH, I, from A to I, all these forces are. Okay. So we'll do one by one. A is a force. Now the plane we are talking about is K. Plane direction is K, that means it is looking upward. So it is the top face. It is located at point Z is equal to Z plus delta Z. So it is not the bottom plane, it is the top plane at a height of Z plus delta Z. Okay. Now what is the shear force at that point? In the x direction it is tau Zx plus delta tau Zx divided by delta Z, del Z into delta Z into del Y into del X. This is the area of the surface. It is the area of the top plane and the shear force. So you multiply the shear force by the area, you get the force on the top plane. This B is similarly the shear force because of tau Zx on the bottom plane, right, and it will be on the negative side. Okay. I have shown here positive because my arrow B there is negative. Okay. So this is located at minus k direction at location z. Minus k direction means plane is looking downward. How do you measure the direction of the plane? If you are given a volume, like any volume, control mass, you take a surface here, take the outward normal. So in our case, outward normal is minus k. Okay, that you can see once you go. Similarly, you find C. This is on the plane zx, or the plane you can say which is in direction z, that means front and backward. Front direction is minus y, the forward direction is plus y. Okay. Similarly, D, that will be on the front plane, C is on the farther plane in the front direction, backward direction. Okay. Now you can see here this D, so A is acting here top, B is acting here at the bottom in the negative direction, C is here in the right direction, D is in the negative direction, negative y on the front face. Alright. Now remember one more thing, that when you draw these angles x, y and z, people might not have told you that there is a rule in it. Because we are doing vectors, so there has to be a particular direction of this. I could have shown y here. But that is wrong. Can anybody tell me why? Why can't I show y on this side? You don't know? Anybody? If you do this y on this direction, you might land up sometime in a blunder. Now I tell you the reason. Reason is, this is an I-axis vector, this is j vector and this is k vector. It is not important what is your I, j, k. What is your important is I cross k should be equal to j. So I cross j should be equal to k. This cross product rule should be followed. Otherwise, what will happen, if you have to do cross product in your solution, somewhere what will happen, you will get a negative answer, and that may not be correct. Okay, so this is what we have to follow. Okay. Now then we talk about normal forces. Normal forces are in x direction, are here. This is E and F. Now this E and F are the normal stresses. Okay. Normally they are same as pressure. In liquid or fluid, this type of so actually pressure is substituted by that, but we are taking it into account here, and if it is not there, we will make it 0, right? So our matrix will be complete. So what is happening is tau xx, this is on the right side, right face, right? The plane is in I direction, located at x plus delta x, and the force is acting on the right direction, because this is not a pressure force, this is a stress. Stresses are always shown outside. Okay, so this is the direction of E. Corresponding is F direction. Again here tau xx on the left plane it is working. Tau xx means what? A stress which is normal to the plane, right, in the x direction. That is the okay. So again it is minus I at location x. Okay. Now then you have also pressure forces. Pressure force is slightly different, they act inside. Okay, so pressure on the right face is P plus delta P by del x into delta x, and on the left side it is P, you multiply area both sides, so G will be in the negative x direction and H will be in the positive x direction. Right. So in a fluid shear forces will be there and pressure will be there. Normal stresses will not be there. Normal stresses come into solids. Right. Suppose I have a pen like this. I can press it like this. If you take any element in between, the forces are normal. I can pull it also. Forces are normal, right? And this is a compressive force, this is a tensile force, right? So they are part of the solid. But when you talk about fluid, you cannot apply tensile force, you cannot apply compressive force. Compressive force is actually a pressure. So we are already taking pressure also. So what we will do, we will put tau xx and tau yy and tau zz equal to 0. That we can do, right? So that is why it is important to know that how the formulation has come, because nobody is going to tell you that what should be the value of tau xx. You have to decide yourself, right? Okay, so that now all these forces are there. Then there is one thing more, is a body force. Body force, so you have a fluid element, control mass system, and gravity, let us say gravity is acting on it. It is acting on the whole body. So that force is actually proportional to the mass. So rho into delta VL is the mass, Fx you multiply, you get the body force, it is taken as I. Now normally it will be equal to, I will be equal to what? Rho delta VL into G, gravity, or you can write equal to mg, and it will be in this direction. But you know your coordinate system is arbitrary. It may not be always minus y as the downward direction or y as the upward direction. You can have x, y, z as like this. And if a vertical force is there, it will have components in all the direction. Right? Just see, if your axis system is like this, and a force here will actually have two components, one here, one here. So these forces, this what we are talking about, rho x is the component of the body force in x direction, and it can have been in all the three directions. So whatever it is, it may be 0 also. If it is x, y and z are so aligned that only y is vertical always, okay, then x is 0, z is 0. Or if it's z is aligned vertical, then x and y are horizontal, then they are 0 in a gravity case. But suppose you are going in space, then there is nothing like vertical direction. If you are passing through any solar body, space body or heavenly bodies, it will attract towards it. So whatever is your coordinate system x, y, z, in that case it can be, the force can be acting anywhere, the body forces. And similarly you can have body forces like electrical forces, right? Magnetic forces, depending upon where is the source, you can have in any direction. Okay, so don't be confused by that. We are doing it for a most generalized case. Okay, now we proceed further. We write conservation of momentum equation in x direction, right?
What is Fx?
Fx is the body force in x direction per unit mass, and that is why you are multiplying it by rho and delta VL. You have to be careful about its units also. Somebody may give you body force in terms of volume. No, it will not work here. Your equation is for mass. Okay, you have to convert it. So that thing you have to take care of. Okay, now for a control mass system, you will find that mass will remain constant. So what I can write is now this equation becomes, because mass is not changing, this becomes m du by dt. So what I will do that, and this m du by dt is equal to sigma fx. I have already written here. Now let us find out what is sigma fx. Sigma is the sum of all these forces. These are 9 forces, right? 3, 3 and 3. So okay, 9 forces. All of them are working in x direction. On the body you sum it up, and when you sum it up you will get these forces. I have already given you equation for all of them. You put it, you will get this. Okay, because A and B will come together, C and D will come together, G and H will come together, and F and G will come together, right? So you will have I and F and G आ जाएगा, I आ जाएगा, P वाला कहाँ गया? We have talked about P. हाँ, P is GH. So ये आपका आ गया AB, CD. There has to be E and F. यहाँ पे मिसिंग है, A B C D, E is missing here. तो ये हो जाएगा A प्लस B, C प्लस D, E प्लस F, G प्लस H and I. Okay, and on the right side you have, this is the mass, this is the rate of change of velocity, and these are the forces. Now you cut out this on both sides, you get this equation. This is a equation of momentum in x direction. Now whether it is conservative or non-conservative, conservative, it is non-conservative. Rho is outside the derivative. Rest all are in the derivative. Okay. So yeah. Now what we do, this is your non-conservative form of equation of momentum. We make the conservative form of it. And as you guessed rightly, you had to do something here. The rest are all already conservative terms. Okay. So now what we do, we already know that this is the equation for local derivative, convective derivative and total derivative, total local convective. Okay. Now what we do, we write du by dt like this. This is for general phi. Phi can be anything. So what I do, I replace phi by u, I get this equation. Okay. Now I multiply this equation by rho on all the terms, right? And then what I do, this A term is actually written in two parts. Similarly, this is also written in two parts. Right? Now then what I do, I take this term and I take this term and this term here and this term here. First from A, first from B, add it up. Second from A, second from B, add. Now this term is what? Continuity equation. Del rho by del t plus divergence of rho v equal to 0. So this term will go away. What is left to you is this. Now this term you replace in the original this. Here it was rho du by dt. In the derivation it was this. So now you look at this equation. Everything is inside the derivative. So this is a conservative form of conservation of momentum equation. So again you have two direct. Okay. Now what you can do, you can just change the subscript. You can write for y, you can write for z also. Okay. So these are three equations which form non-conservative, and this is three equations conservative form. Alright, and we can go a step further. We can write these three equations together as a single equation, but that would become a vector equation. So what is a vector equation? It's actually basically three equations put together. In a vector equation, if you separate the x, y, z component, these are three equations. Or if you put the three components together, it becomes a vector equation. So we are going to do that, and I'll prefer to do it slightly, and reason being that we will close with this. So this chapter will also be closed. Okay. Will take only hardly 5 to 7 minutes, and this will be over. Now What we are doing is, this is again pure mathematics, no physics in it. Okay. So what I do now, what I have done is I have written both the equations together. This is in non-conservative as well as conservative form, both. If I take on the left this one, it is a non-conservative form. If I take these two terms on the left side, it is conservative form. The right side remains same. Now then, why I am doing it? Because I want to do for both of them together. Instead of doing separately, I am doing it for together. Now then there are three equations here, 1, 2 and 3. In fact, there are 6 equations here. 2 equal sign in each equation. So 2, 3 and 3 is 6 equation, and 3 of them are conservative and 3 of them are non-conservative form. Now the first term in each case I have said is A. Second term I have numbered as B. Third term as C, and this fourth set is taken as D, and fifth is taken as E, sixth is taken as F. Right? You can say this is the X part of F, this is the Y part of F, and this is the Z part of F. You can say this is AX, AZ, AY and AX. Okay. Now what I am doing is, I am actually adding all the A parts together. AX, AY, AZ. This is A. AX, AY, AZ. And you can write all of them together as this. Okay, because this is 3 velocities. Similarly, you take B part, and B you will have these 3 terms, X, Y and Z. You add them up in a vector form, you get this. Same thing you do with C. Same procedure for all the terms. You have this, you have this, and you have this. Now you see that here, this is a sum of 3 terms, this is a sum of 3 terms, okay, and this is also a sum of 3 terms. So total there are 9 terms. They are X, they are Y and they are Z. So I have written them here, X, Y and Z, 3 components. Now these 9 terms can be written like this. So all the 9 terms have been put in one symbol. How? You have I and J. I and J are basically 1, 2, 3. I, J, K. These are equal to 1, 2, 3. 3 axes, I, J, K. So U1 here, you are seeing here UI and UJ. Instead of using U, V and W, I am using U1, U2, U3. And then U1, U2, U3, this is U1, U2, U3 is actually equal to U, V and W, and I am putting all of them together as UI. So depending upon the value of I, it is either U, V or W. Similarly, X1 is taken as X, X2 is taken as Y, and X3 is taken as Z. Xi is nothing but X1, X2, X3. And again they are nothing but X, Y, and Z. So you can match it, you will get this. Okay? And this is also vector I, showing the direction. So I, J, K, this is the I direction, this is the J direction, this is the K direction. So you keep on changing I, J, K here. There will be 9 terms. 3 will come here for J equal to 1, 2, 3. Then 3 again terms will come for I equal to 2. It will be J 1, 2, 3. then again I equal to 3, there will be 3 terms, j 1 2 3, right, and they will be arranged like this. Okay, nothing, no physics, simple mathematics. Okay, and you have to do it on your own. Then if you talk about D term, D is again having set of 3 terms. So this is the x component, this is the y component, this is the z. You put them all together, you get this 9 terms in one summation sign. Okay, and same rule applies here for xj, I and tau ij. Okay, that is just a jugglery, you can see yourself, and those terms you have put. Now when you talk about pressure terms, E terms, you put all of them, this becomes gradient of pressure, right, and then you take this body forces, it becomes rho f. Now this will be, in our case, maybe will be G, right, and then you can write this equation. This is one equation, non-conservative form, all the 3 equations put together. Okay, and similarly you have this equation where this is a conservative form and all 3 equations put together. When you solve this, you will find that this is a vector equation, right? Vector terms will not go away, they will form set of x, y and z terms, separate them and you get 3 equations. Okay, so this is what your equations are. Okay, so we will stop here.